Adriana. Just a little note of Adriana's talk. So for Adriana, dark matter remains one of the most compelling enigmas in physics, gravitationally inferred, yet not directly detected. In this talk, she will be presenting a unified perspective linking kinematic, geometric, and particle level approaches to understanding dark matter at galactic scales. So Adriana, if you would like to, give yourself a little bit more of an introduction, and I will mute myself. And we're excited to listen to your presentation. Thank you again.
So thank you very much, Ryan. I wanted to thank everyone watching this seminar. I just wanted to also add that this is like a side project that I continued after finish my bachelor. Okay, now you can hear me. So I wanted to, as Ryan said, I want to present a unified perspective combining the kinematics, the geometry, and the particle perspective of dark matter to understand what it is at galactic scales. So let me start maybe with a little bit well, here you can see the outline of the talk, and I wanted to tell you that it's been 90 years since Fritz Zwicky first realized that galaxies were moving too fast in the Coma cluster, and that the only way to understand this was if there was some kind of missing matter that could only be inferred gravitationally. And this is what we call today dark matter, but initially dark matter was a term that was used to explain or to describe baryonic matter that could not be seen in our galaxy. But with time, this term evolved, and nowadays it is used to describe what accounts for an 80% of all our universe, of the matter of our universe, the unseen matter, not the baryonic one. So I wanted in this talk to make a combination or just show different perspective and combine them. So I want to talk about the kinematics in galaxies, the geometry of dark matter halos that might surround galaxies, and also to talk from the particle perspective that we observed in neutrino telescopes. So let me start by giving a very short history of dark matter, but I want to make a point, so it will be very fast. So the humankind has been interested in the cosmic order for millennia. So it might have been first Aristotle who put the center as the Earth at the center of the universe, to then have a few centuries later Galileo changing this perspective after making observations. And this is precisely what dark matter is about: measuring or observing with technologies, making observations of the motion of the universe, the motions in the universe, and try to understand what we cannot see with the naked eye. So then it wasn't until 1687 that Newton first created the tools to actually be able to convert this motion into mass, and that astronomers were then able to talk about the universe in terms of gravity. And these astronomers were then able to track the motion of bodies to actually be able to understand some mass that they were not able to see. And one of the first ones to do this, but some time later, after Newton actually wrote this book, was Friedrich Bessel. He was studying the faint stars, faint companion stars that he was not able to see, but he could infer the existence of these particles, these bodies, due to the wobble in the motion of the stars. And this is what, by the time, they called dark masses, not because they were made of dark matter, but because they could not see them directly. So at the end of the 19th century, we have the scientific community talking about dark stars, dark nebula in the Milky Way, because they want to study the matter that is in the Milky Way that they cannot see, but that they can infer through motion. And this is the first time that the term dark matter is used, although it was used in French, matière obscure. And this term was really not used to describe dark matter, but rather matter that we were not able to see, but nothing exotic, just maybe meteors or dust. But it was not until 1930s that Fritz Zwicky, using the virial theorem, studying the coma cluster, realized that yes, galaxies were moving really fast, and this wasn't possible if there was not some kind of invisible mass, as I was saying at the beginning. And at the same time, Sinclair Smith, when studying the Beriego cluster, although no one talks about in Sinclair, they only talk about Fritz Zwicky, but they were both observing the same and making the same assumptions, only none of them wanted to really accept the fact that there was some really, really huge factor of the matter that was not seen. And then after World War II, we were able to use these new technologies, the radio technologies that were developed for the astronomy field. So we were able to use these technologies in the astronomy field, and until now we had observed the universe using stars. But after this, we were actually able to track all the hydrogen in the universe and be able to map the mass distribution of the galaxy. And then in 1959, these two astronomers realized that the Milky Way and Andromeda were moving against each other really fast, faster than if there was only to account the visible mass in the local group. So they thought about the idea of having some kind of continuous medium to which the Milky Way and Andromeda galaxy and all the galaxies in the local group were bound, that actually made them interact in this way. But then we have, well, then we arrive to the 60s and 70s. I swear this is my last slide of history. And we have Vera Rubin and her collaborators who used spectroscopic techniques to measure the rotation curves in galaxies. And then they realized something really interesting. Rotation curves do not decrease at the end of the galactic disk. This would make sense. This would make sense if there was more mass outside of the galactic disk. But if all the mass is concentrated inside of the Milky Way disk and at that radius, we would expect to observe some kind of decline in these rotation curves. But this was not what they saw and not what we see today. Actually, around that time, Einasto and collaborators realized that galaxies, well, they assumed and stated that galaxies were surrounded by massive coronas. So after all these publications, after this moment in time, we start describing and explaining all these observations, assuming that the standard is to have dark matter surrounding galaxies in the shape of halos. And then in the 70s, 80s, we start creating N-body simulations, and we realize that in order to actually be able to explain the structures that we today observe in galaxies and in clusters, we need a very large component of non-baryonic matter in these simulations, which would be the dark matter idea. It's needed. And then sometime later, we measure we make this large redshift surveys that actually show us that the universe at large scales looks like a cosmic web. So it's made of filaments, walls, nodes, and voids in the same way as simulations when we consider this component of cold dark matter. Sometime later, we were able to actually measure the CMB anisotropies, and we realized that 25% of the universe is this kind of unseen matter that we cannot observe and barely measure, only through gravitational waves. And only this 25% is 5 times more than only baryonic matter. So I want to end, as I told you, this is where I end the history part, this summary with this sentence here. From the orbits of stars to the pattern of galaxies across billions of light years, the story of dark matter is written in the motion and structure of the cosmos itself. So yes, if we want to understand the nature of dark matter, maybe it is necessary to actually map how and where this matter is distributed. Okay, so until here, the history. Now that we have talked about how dark matter emerged historically and also how we can infer it gravitationally, let's talk about what it might be, maybe physically. So, what is dark matter made of? We have three hypotheses. The first one typically is to, well, the first one, not typically, is to assume that dark matter is made of baryonic compact objects, for example, a brown dwarf or a primordial black hole. The problem is these bodies, these microlens in service are very constrained, and macroscopic objects would only make up for a small fraction of dark matter. So we need something else. Then we have the microscopic perspective. And I will talk about this one later, but the idea is that we have models that well, we have fields, and these fields create we have particles, and dark matter would be this either WIMP particle, axion, sterile neutrino, and we could maybe be able to measure it in direct, indirect, or collider searches. I will talk about this one a bit more in a second, but first let me introduce the third hypothesis. The third hypothesis is to consider dark matter as a fluid, a coherent fluid that fills the universe and makes up the geometry or the skeleton of the universe. And then dark matter would be described through an equation of state of the density and also a velocity field. I'm not an expert on this, but I think it is very interesting. So let me talk about the microscopic particles perspective. So the idea here is that we have some dark matter particle model, let's say a WIMP model, because that's the one we searched for at KM3Net experiment. I will introduce it in a second. So we could look at it from three perspectives. So we have collider searches in which we collide, for example, protons and create particles, and maybe from these collisions we can create a dark matter particle that we would observe from a missing energy plus visible particles. Then we have direct searches where we expect dark matter to arrive and interact with nuclei or electrons in the detector, and then produce, scatter of target nuclei or electrons. And then finally, we have the indirect detection one, in which dark matter either annihilates or decays somewhere in the universe, and we can observe an excess of gamma rays or neutrinos, so decay products, an excess of decay products. So this is precisely what we do in KM3Net. KM3Net Neutrino Telescope is an array that is located, an array of optical modules attached to lines that we have inside of the Mediterranean Sea. And with that, what we do is we measure the light that particles coming from interactions of neutrinos leave inside of the sea. So we have two detectors. We have ORCA, which is located at the south of France, and ARCA, which is located in the south of Italy. Both of them share the same technologies, so it's also, both of them are strings. The difference is ARCA is very sparse, ORCA is very dense. Therefore, they cover different energy ranges. ORCA covers low energy ranges, and that's the one with which I have been doing my analysis until now. ARCA covers larger energies. So talking a bit about how we do dark matter searches, just to introduce it, we expect dark matter to maybe accumulate at places of high densities. Maybe this could be the galactic center. Then dark matter annihilates and produces some particle. This primary particle could be, for example, the tauon. The tauon is not stable, so it will eventually decay into maybe neutrinos. And neutrinos might travel to the Earth, and in their way, they might interact with something close to the detector, and we might observe them, many mites. So the idea here is that we observe some kind of a neutrino excess coming from the dark matter annihilations in the galactic center. So this signal depends on the density profile we use. We typically, in this analysis in KM3Net, use the Caspi-Navarro-Frank-White density profile. And the thing is, if we have a very dense cusp in the galactic center, this would strongly enhance the annihilation flux we observe. And this would be very interesting. So the idea is to look at the galactic center because it's the densest place where we think there's a larger quantity of dark matter particles. We look for an excess of neutrinos coming from WIMP annihilations, and our background are atmospheric neutrinos, so we have to model them and try to reduce the background. And eventually, our analysis, so these are the results that we obtained for the summer conferences, in this case, ICRC in Geneva, and the alkalines here in black are the results from a colleague of mine, and the ORCA results are my results for ORCA 6, 10, and 11 strings. So our experiment is not fully built yet. We are building it, and as we build it, we take data. When we observe no significant excess what we do is to place a limit. And this is typically what has been happening with all the experiments that are searching for particle dark matter. They haven't obtained some excess or signal that tells them that there's dark matter, so we have drawn this limit on the annihilation cross section. Since the particle picture still remains elusive and we are going to even more and more weakly interacting ranges, this motivates us to go to look at larger scales. And this is where my real talk starts. It only took me 15 minutes to get here. So let me talk about the maybe clearest observational evidence of dark matter, which is at rotation curves. And as I told you initially, if there was only matter inside of the galaxy, then we would expect the velocity profile, so the rotation velocity, to decrease as we go away from the galactic center. But we observe that it actually stays constant. It doesn't decrease in general, what we observe. Some galaxies do. And this is what we know as rotation curve problem. So we have what we expect. We expect a Keplerian taper. If there's only baryonic matter, we should observe this decline in velocity. But numerical simulations have told us that the halos, dark matter halos, should show a Navarro-Frank-White profile. When we calculate the velocity of such a profile, we actually observe that at large radii, the behavior of this velocity is very similar to a Keplerian taper, but modulated by a logarithm. So it's in the case of the Milky Way, if we use Navarro-Frank-White, our Navarro-Frank-White profile with some values from a fit that someone made some time ago, the rotation curve of the Navarro-Frank-White dark matter rotation curve, not the whole galaxy, only the Navarro-Frank-White, would look like this. And there would be some kind of a taper at large radii. So in this paper that we uploaded to arXiv very recently, we tried to check if 175 galaxies, late-type galaxies, so spiral and irregular galaxies in the Spark database, we want to check if they prefer a Navarro-Frank-White taper, which is our alternative hypothesis, or if there is a preference for a constant rotation curve. So we will be doing a statistical analysis of the slope of the outermost data points. So this is very important. The first step is not only to select galaxies, we want to select the end of the end of the rotation curve. So for that, we have a way to three criteria. So you can see them here. The first condition would be that the first condition is that we are outside of the growing part of the rotation curve. Okay, so the black points are discarded points. The second condition is that the baryonic rotation curve is smaller than the dark matter rotation curve. And the idea here is basically to get rid of all the baryonic contributions that we can, because it might be larger in the center regions of the galaxy. Then the third condition will be to have a velocity profile where the baryonic curve is actually decreasing. So in these plots, you see examples for the two galaxies. The blue curve is the rotation curve for the baryonic components of the galaxy, which can be inferred from the visible light components. Then you have the black points and red points. The red points are when the selected points after using this criteria. And these are the data points of the rotation curve that are measured with the hydrogen lines. And then we can infer the dark matter red dotted dashed line from this equation here. So using the rotation curve and the baryonic rotation curve. And then what we do is we fit the dark matter curve to this very simple linear function here. And we then calculate this slope here doing, well, minimization. And in these two galaxies, what we observe is that the slope of the dark matter rotation curve is increasing in both of them. So what we will do is we do this selection with all the galaxies in Spark database. Some of them will be discarded, and then we do a statistical analysis of the slope, so of the slope of the outermost points. We observe that when we consider conditions 1 and 2, it is less constrained, so we have more galaxies, out of which 46 are decreasing. And in the case in which we consider also the third condition, we will have less galaxies. And what we observe is that when making an analysis of these slopes, the data are not consistent, or not the second hypothesis is not consistent with the preference of the dataset. So what we observe is that Spark database and the galaxies that are selected actually prefer a flat rotation curve over a Navarro-Frank-White taper. And this is the case for Spark, but it is not the case for the Milky Way. So we have the measurement of the Milky Way rotation curve, although this is more challenging because we are inside of the Milky Way, so measuring the Milky Way rotation curve is very challenging. We have the rotation curve from 2020, which is in black, and then we have a few measurements from 2023. And what we observe is that in all of them, the slope, when we make a fit of the dark matter rotation curve that we can infer, the slope decreases with some Keplerian taper. And this is very different from the Spark database. But the idea here is, in the Spark database, the results are consistent with a flat rotation curve. And this actually suggests that there might be a halo that is more than just spherical. So maybe we are talking about an elongated structure. And this actually takes me to my second point, talking about the shape of dark matter halos. And here I want to talk about a work that we published in 2023, in which we were also analyzing this Spark database, but with another idea in mind. We wanted to study the shape of the halos from the galactic plane. So typical solutions to the rotation curve problem are two. Either we modify the mechanics, which is great, but typically this doesn't solve other observations at other cosmological scales. The second and most usual option is to modify the gravity source. Usually we put a spherical dark matter halo around a galaxy. And a spherical dark halo is great because in a two-dimensional cosmos, we would observe constant rotation curves. But if we have a spherical gravitational source in a three-dimensional cosmos, we would expect a decrease, a Keplerian decrease. But this is not what we observe. We observe something that is happening in a two-dimensional cosmos, and we definitely do not live in a two-dimensional cosmos. So in this case, one idea is to actually achieve some dimensional reduction, considering maybe an elongated source. So let me give you this toy model where we have a cylindrical halo, a filamentary halo, in a spiral galaxy. In this case, you will see that the rotation curve will increase, and then once we are outside of the cylinder, this rotation curve will be naturally constant. This was great, but what's the idea behind this? So The thing is, we typically talk about galaxies as isolated systems. But the thing is, galaxies are not isolated, they are always interacting with other galaxies. Actually, if we zoom out a bit, we realize that the universe is a cosmic web made of filaments and made of nodes where there's a larger density of galaxies. So why do we keep thinking about galaxies as independent items when there might be some interaction with this cosmic web? So the idea is this: what if dark matter halos exist as a two-component system? So a core that collapsed earlier in a gravitational way and maybe is spherical or maybe has a rather triaxial shape, and then some kind of connection and interaction with the dark matter filaments that explain this behavior that sometimes we cannot explain with just a spherical component. So this is where all the idea comes from. So the thing is, to actually explain a constant rotation curve in a galaxy, we need either a spherical shape, so a spherical halo with a very fine-tuned isothermal profile, or a cylinder, and a cylinder with any kind of density profile, because the flattening is achieved naturally. But we can also go to a rather intermediate case, so maybe a triaxial halo. And this is exactly what we did at this paper, which was to make a multiple expansion of the gravitational potential, impose axial symmetry and reflection symmetry on the galactic plane. And then we calculated in a numerical way the rotation curve. And in this way, we realized, well, we considered two kinds of density profiles. We had a step function and then a Wood-Saxon density profile. The idea was to use a step function, but with a smoother step. And what we realized is that in both cases, both density profiles, as we added larger factors to this multiple expansion, so as we added more factors, we were able to actually explain this flattening at the end of the curve, but only with the zero component, so the spherical halo, we didn't achieve this flattening. So what we did, well, we did this ranking here of the models from best to worst, and we realized that the models that work better are those that consider very elongated sources, and the ones that were working worse were those in which the sources were spherical. And here in this plot here, you observe this ellipticity value that we were able to calculate from these halos. And you can ignore the y-axis because it's the number of the galaxy, but the x-axis tells you the ellipticity value, where c is one of the axes, the length of the axis on the galactic plane, and a is the axis of the dark matter halo on the vertical axis. And when this sphericity is 1, we have a spherical halo. When it's below 1, it's prolate, so elongated. But when it's larger than 1, we have a flattened system, so an oblate halo. And it was clear to us that there was some kind of preference for prolate halos from galaxies, from rotation curves. But there was also a problem here because we were not able to distinguish between spherical halos with an isothermal profile from elongated halos with an arbitrary profile, because we were looking from the galactic plane, and we were also not able to constrain a value for the semi-axis along the z-axis. We were able to constrain to tell we were able to tell that it was an elongated source, but we couldn't tell how elongated because we could not see a decline in the rotation curve. So this is how we decided to go to out-of-plane observables, such as stellar streams. And this takes me to the second part of this talk. After working with rotation curves and realizing that we could not really realize how prolate they were and distinguish them from a spherical source with an isothermal profile, we turned to stellar streams. Stellar streams are stellar streams, imagine we have a cluster of stars or a dwarf galaxy that falls to a gravitational potential of a galaxy, and then it starts to be tidally disrupted and elongates and stretches. So this is what the stellar stream is. It ends up being a line of stars or a stretched cluster of stars moving around a galaxy. And the idea was to treat these halos as a curve and calculate their torsion. For that, well, the torsion would tell us how sharply these curves are twisting around. And to calculate the torsion, we need to calculate the tangent, the normal, and the binormal vectors. And the torsion would actually be the variation of this binormal vector around the curve. So the thing is, what does this tell us about the shape of the halo? Well, this tells us the value of the torsion tells us something about the shape of the dark matter halo. When we have a spherical source, the orbits move on a plane. Also, the stellar streams, they move on a plane. They will not move from this plane. And the variation of this binormal vector will be constant on the plane. So the variation actually is zero, so we have a null torsion. But if we have a cylindric source, what we realize is that this torsion is constant because the variation of the binormal vector on the curve is also constant. You can do the calculations yourself, but don't do them. Okay, so what we wanted to do is to make a few simulations, understand what the torsion was, taking into account one on another gravitational source, and then compare this to real life things, such as stellar streams in the Milky Way. So yes, I created this very simple n-body simulations using 1,000 stars, and we put an initial cluster at a certain distance from our galactic center, and we allowed them to evolve over time under some kind of a potential. For example, here I am talking about a spherical gravitational field. So then what we do is we take pictures at different times, and then we observe how they look. And this is how the simulation looks after we finish. So after we stop the simulation, there are different points of view here. So this is the XY axis, so I'm looking from above, and the XZ axis and the YZ axis. As you can see in the spherical source, we have that the stellar streams are moving on a plane. In this case, it is tilted. And what we also see is that as we go to larger times, we observe that this cluster is actually stretching and it's turning into what we know as a stellar stream. Of course, these are very simple n-body simulations, not like there are very complicated ones that are very accurate, but this was just a simple test. The second part was to take these streams that we simulated, fit them to a parametric curve, such as the one you can see here, and calculate the torsion that we would expect. And this is very interesting in the case of a spherical halo. So here you have a simulation. You can see how the streams lie on a plane. We realized that our torsion in a spherical halo would be of the order of 10 to the minus 3, 10 to the minus 4. Then when we go to a cylindrical halo, in the simulations, we could give initial pushes in different directions. When doing the simulation, we could actually add some random velocities. And in the cylinder case, when you gave like an initial velocity towards the Z direction, it started moving helicoidally around the cylinder gravitational potential. And when measuring the torsion of the streams, we observed that in most cases, the torsion was of the order of 10 to the minus 2 inverse kiloparsecs. And then we also tried to study how these simulations would look in a combined system of some kind of a cylindrical halo and a spherical source, so cylindrical and spherical source. And we realized that both behaviors were combined. So the streams tried to move on a plane, but at the same time were rotating around the source. Well, in this plot, you can actually check that it is not only lying in one plane. And finally, to actually do our simulations on some real data, we need to understand what our background is, because we don't only have a halo, we also have a galactic component. So if we assume that this component was a galactic disk and then there is some kind of a spherical halo, our zero torsion, our background torsion, should be of the order of 10 to the minus 4. The spherical motion, the motion due to a spherical halo, would be moving, the orbit moving around plane, in a plane, but then the galactic disk causes a small oscillation around this plane. And when we calculated the torsion, it was of the order of 10 to the minus 4. So anything above this value would mean that there might be some significant dark matter contribution that was not spherical. So these are all the cases that we studied. And well, calculating the torsion in this case, the combination is not so simple, and it's definitely not 10 to the minus 2. But then we decided to go to the real life scenario and to take stellar streams from the Milky Way. And we used this software from Cecilia Mateo, which is not a database, but they store the coordinates of certain streams. And we chose only those streams that were far away from the galactic center to avoid some interaction with baryonic components. But we also got rid of some streams that might be too close to the Large Magellanic Cloud, which is actually deforming some streams. And well, it was a bit complicated. The thing is, we ended up with these streams here. And the idea is that if streams are at distances of 30 kiloparsec, we expect the torsion to be of around 0.01 kiloparsecs inverse, so inverse kiloparsec. And if anything is above this value, there might be some significant contribution of a non-spherical gravitational potential. And we observed that a few of these streams showed values above around this expected zero background value, which was pretty interesting. But we decided also that this was really interesting as a new observable. And in the Milky Way, it is very doable. There is also a group in Princeton doing this with extragalactic streams, which is very, very interesting. It's also very challenging because the extragalactic streams are two-dimensional images, and they don't have the third coordinate, so they can just talk about curvature instead of just talking about the torsion. But it's really interesting. So just putting everything together, let's talk from a more geometric point of view. So instead of talking about how much matter there is in the universe, or let's ask what is dark matter? And we can understand dark matter, changing a bit the perspective, as the geometric residue of the universe's mass distribution. So once we get rid of the baryonic component of the universe, dark matter could be what is left, the skeleton of the universe, the geometry that sustains everything. And this is where rotation curves, halo shapes, stellar streams, and other things of this kind actually allow us to measure this geometric residue. So yes, putting everything together, well, I wanted to to combine three different perspectives. So, on one side, I wanted to talk about the kinematics of galaxies. If rotation curves remain flat, we may need some increase in mass function away from the galactic disk. From the geometric perspective, stellar streams show some significant torsion that might need of more than just a spherical halo surrounding the galaxy. And there seems to be a preference along the Z axis, but this is very interesting to explore it with more depth and more data. And finally, from the particle perspective, we observe that we are not only neutrino experiments, but also other experiments, we are pushing dark matter to to very weakly interacting regions. In the future, maybe we even consider studying dark matter as a fluid. And so, yes, to already close this seminar, we realized that dark matter does not seem to behave like a gas of particles, but it rather behaves as a continuous medium, coherent, filling up the universe with a trend to have some preference of an axial symmetry, at least in galaxies. What results in stellar streams and rotation curves are compatible with the Landau-Basinian cosmology model, but they challenge the cold dark matter picture, as the cold dark matter picture expects um, a halo that collapses gravitationally in a spherical way. And maybe tells us something about some interaction with this cosmic structure. Maybe there is some baryonic feedback that is kicking matter away, or maybe there are some kinds of interaction inside of the halos that we cannot comprehend yet. And then finally, rotation curves have more information than just the amount of dark matter that we can measure in them. Rotation curves and stellar streams allow us to study more about the geometry of the universe itself and maybe tell us something about the nature of dark matter. So this is very interesting. Finally, I just want to leave this question for the future. Is dark matter a particle, a field of art, or a geometry? And with this, I end this seminar, and thank you for your patience.
Awesome. Thank you very much, Adriana, for that talk. That was very interesting. So for anyone who is in the YouTube stream, if you have any questions for Adriana, feel free to put them in the chat right now. I'll read them out. And then if anyone in the Zoom call has any questions, feel free to put, I think Taiki has their hand up. So Taiki, take it away for the first question. Never mind. Taiki was putting their hand up for clapping. My bad. Sorry there, Taiki. Okay, well, while we wait to see if there's any questions that come in from the YouTube live stream, I had a question. I found it really interesting, the different geometries with this cylindrical and then also the prolate sphere. You talked later on about simulating the torsion with spherical and cylindrical coordinates spherical and cylindrical geometries for dark matter. I wonder if you guys ever did prolate geometry for those simulations, or if those would have just been the same as the spherical geometry in general.
A prolate, you mean an elongated?
Yeah, sorry, yes, I meant elongated. So the
No,
prolate
no,
sphere that was
just to make
elongated.
sure. No, yes,
Yes.
yes. Well, we didn't go to very specific shapes. We rather observed the maybe most extreme examples, which is the sphere, the cylinder, and a mix of both. But I guess that something that was elongated but finite, not a cylinder, would rather look like this, right? There we didn't do it because this was a test study with more general shapes, but we should expect maybe something like this. We would expect the stellar stream to move around it helicoidally until it reaches the top and then maybe turn around or something like that. I guess I would say.
Awesome. Thank you so much.
Thank you.
Is there anyone else in the Zoom call who has any questions? Feel free to put your hand up. And then we got some claps over in the YouTube live stream. Just wanted to let you
Ah.
know there. Another question I have, maybe if we're waiting, if in case anyone else has any questions. You talked about how for the neutrino telescopes, how depending on how spread out the arrays were, that could or that would um define what energy levels that the neutrino telescope could be measuring for neutrinos. Do you know a little bit more about how that works, how the spread of those arrays contributes to the energy levels of neutrinos that we're able to observe?
Um, I mean, in the end, it's basically about being able to contain the stream and measure it. So your question is about how we reconstruct the signal?
It was more so just, as you can see here in this slide, Orca and Arca both have different energy levels that they're looking at. And you said that they use the same technology, but the biggest difference is one is more dense in the arrays than the other, and that can help with the defining what energy levels that it's able to measure for neutrinos. And I was wondering if you knew a little bit more about that
Oh,
as to why.
well, I'm not a super expert in this, but I guess if we maybe think about a very energetic lepton coming, for example, a muon coming from the interaction of a neutrino with water, if it's very energetic, it will probably leave a lot of light in the detector. And Orca will probably not be able to see it because Orca is really small and the light would I don't know how to say it in English, but it's too much light. So in case of we have Arca, Arca is sparser, so it would be able to maybe so measure the individual hits and not all of the photomultipliers of the detector would receive the light. I'm not, I don't know if I'm explaining myself. If we have like a signal, like neutrino muon crossing it, so if the neutrino is very energetic, all Orca would lighten up. And if we had something that was sparser, we would be able to recover the signal better, maybe. That's why what I mean that we Arca, for example, covers larger energies. Actually, the very high neutrino event that was measured a few years ago, but publicly made available this year, um, was actually measured in Arca, and it was very, very energetic. So it was also maybe too energetic for Arca. I don't know if this answers your question.
Oh yeah, it does. Thank you so much. I'll give it a few more seconds if anyone else has any questions. Okay, it's looking like we're all good on the end of the questions. So I'd like to finish off by thanking Adriana for giving us that awesome presentation on, yeah, the on dark matter, on what potentially its nature could look like, whether once again it's particle or geometry. That was very interesting. And I know a lot of people over on the live stream really enjoyed it too. So thank you so much for giving us that presentation for this month's HQP seminar. Really appreciate it.
Thank you very much for making it possible.
All right. Well, thank you everyone for also attending. I will be ending the live stream now. Enjoy the rest of your Wednesday and hope everyone has a happy Dark Matter Day in 2 days. All
Thank
right.
you.
Bye, everyone.